Section 6.12.1 Isentropic turbine efficiency. In these sections, we are going to study the thermodynamic performance of steady flow devices such as turbine, compressors, pumps, and nozzles. We'll evaluate the best performance we can get from the device and determine how well the actual device performs compared to the ideal device. First, we are going to take a look at turbines. Turbine is a work-producing device. It converts the kinetic and potential energy of a fluid to a useful work. Turbine may be considered as a steady flow device. It means that the states of the fluid at the inlet and outlet remain constant with time. For example, mass flow rates and properties such as pressures and temperatures at the inlet and outlets are constant with time. The energy balance can be simplified for steady flow turbines. This is our turbines. Location 1 is here at the inlet of the turbine. Location 2 is at the outlet of the turbine. It is operating under adiabatic conditions. So Q dot drops out. There is no heat transfer across the boundary. We neglect the kinetic and potential energy changes in the system. So the work output per unit mass flow rate is the change in enthalpy. The isentropic efficiency of a turbine is defined as the ratio of the actual work output to isentropic work output. So the isentropic efficiency, eta for turbine, is defined as the ratio of actual work output to the isentropic work output. The actual turbine is not reversible. It contains irreversibilities. The isentropic turbine is an ideal device, so you may think of isentropic work output as the maximum work output at a given condition, because the isentropic process is a reversible and adiabatic process. So the isentropic efficiency is useful to set the theoretical limit of performance for turbines. It is a measure of the effectiveness of the process, showing us how the actual device performs relative to the ideal device. So we can compare the actual turbine with the ideal turbine and determine the degree of inefficiency in the actual device. So what we are comparing is between the actual and the ideal condition. The work produced by a turbine would be greater in the ideal condition. So the value of isentropic efficiency should be less than 1. Let's see the process on a HS diagram. Y-axis enthalpy, x-axis entropy. The location 1 is in the inlet of the turbine and the location 2 is at the exit. This is the constant pressure line. This is another constant pressure line. P2 is lower than P1. This is constant temperature line, T1. The state at the inlet is here, 1, at temperature T1 and pressure P1. And we are only given the pressure at the exit, pressure P2. So we should note that the state of the fluid entering the turbine and the pressure at the exit are fixed. They are identical for both the actual process and isentropic process. At the inlet, the fluid properties are predetermined before the fluid enters the turbine. So the state at the inlet is fixed. At the outlet, the pressure is determined by the surroundings where the fluid is leaving. So the pressure at the outlet is also fixed. But that is the only fixed property at the exit. Then what is the difference between the actual process and isentropic process? The actual process accompanies irreversibilities. So it has greater entropy. Then what is the most amount of work produced between the two pressures? From these relations, we know that work is proportional to the enthalpy change between the two states. So H1 is here, H1, and we need to determine the H2. We want to make H2 as small as possible for the maximum work. So that is H1 minus H2S when the process is isentropic. So 2S is here, and enthalpy at state 2. So isentropic process goes from state 1 to state 2S, going vertically straight down. So H2S is the enthalpy value at the exit for an isentropic process. It's an isentropic process, so S1 equals S2S. The actual process has greater entropy at the same exit pressure due to the irreversibilities. So H2 is the enthalpy value at the exit for the actual process. State 2 for the actual process is here. And the entropy here is S2. So S2 is greater than S2S. And at state 2, enthalpy is H2. So H1 minus H2 is the actual work. And H1 minus H2S is the isentropic work. As we expected, the isentropic work is greater than the actual work. Isentropic turbine efficiency is H1 minus H2, which is the actual work, divided by H1 minus H2S, which is the isentropic work. Example 6.11. A steam turbine operates at steady state with inlet conditions of 5 bar 320 degrees Celsius. Steam leaves the turbine at a pressure of 1 bar. There is no significant heat transfer between the turbine and its surroundings, and the kinetic and potential energy changes between the inlet and exit are negligible. If the isentropic turbine efficiency is 75%, determine the work developed per unit mass of steam flowing through the turbine in kilojoule per kilogram. We need to determine the actual work from the isentropic turbine efficiency. So from the definition of isentropic turbine efficiencies, this is the actual work output per unit mass flow rate divided by isentropic work output per unit mass flow rate. The isentropic work output per unit mass flow rate can be expressed in terms of enthalpy. enthalpy change from state 1 to state 2s. So H1 minus H2s. So at the inlet, steam entered the turbine at pressure 5 bar and temperature 320 degrees Celsius. And here enthalpy H1, and at the exit we know the pressure 1 bar. That is the only given property. But we know that it went through isentropic process. So S1 equals S2S. So S1 can be found here, 7.5308. So we know two properties, pressure and entropy at the exit. So pressure 1 bar and entropy 7.5308. So it falls between these two entropy. So we can interpolate to determine enthalpy. So enthalpy 2S can be calculated. So we put the numbers. Isentropic efficiency 0.75, H1 minus 2743.0. So we can determine the actual work produced by the turbine. Example 6.12. A turbine operating at steady state receives air at a pressure of 3 bar and temperature 390 Kelvin. Air exits the turbine at a pressure of 1 bar. The work developed is measured as 74 kJ per kilogram of air flowing through the turbine. The turbine operates adiabatically and changes in kinetic and potential energy between inlet and exit can be neglected. Using the ideal gas model of air, determine the isentropic turbine efficiency. So at the inlet, we know pressure and temperature, so we can fix the state. At the exit, we only know the pressure. And actual work produced by the turbine is also given. And we need to determine the isentropic turbine efficiencies. So state 1 is fixed. When it goes through isentropic process, it goes straight down. And at state 2, the pressure is given. This is the constant pressure line, 1 bar. State 2S is here. So entropy S1, S2S are the same. So this is isentropic process. For the actual process, state 2 has greater entropy. This is S2. And the isentropic efficiency of turbine is defined H1 minus H2 over H1 minus H2S. At state 1, isentropic efficiency of turbine is defined H1 minus H2 divided by H1 minus H2S. H1 minus H2 is given 74 kJ per kilogram. H1 can be determined since we can fix the state at the inlet. Now we need to determine enthalpy at state 2S. So we know that S1 equals S2S. And we also know the pressure at the exit. But take a look at table A22. Entropy is not given. Instead, standard entropy is given. For ideal gas, entropy is not only function of temperature, it is also a function of pressure ratio. So what we are going to do is to use the relative pressure. PR2 over PR1 equals P2 over P1. And this is for isentropic process and air only. Relative pressure is only function of temperature, and we know P1 and P2, and we know the temperature at the inlet. So we can also determine PR1. So we can solve it for PR2. From PR2, we can determine H2S. So PR2 is P2 over P1 times PR1. 1 bar divided by 3 bar. PR1, temperature at the exit is 390 Kelvin. So PR1 is 3.481. So PR2 is 1.1603. And the relative pressure 1.1603 is between these two numbers. We can interpolate to determine H, enthalpy. So H2S is determined. And go back here, 74 divided by. So the isentropic entropy of the turbine is 0.7. This means that the actual turbine is 70% efficient relative to an isentropic turbine with the same given condition.